Okay. Excuse me, welcome back to Top 1 Honors. Today we're going to talk a little more about the chain rule. Actually, we're going to talk a lot more about the chain rule. It's a fairly busy day, so I just want to get in and get moving. Close the door. All right, let's do it. Now, we did set the exam date last time, right? The exam date is the 10th. So I just want to remind you. That's a week from today. So I'll go ahead and drop you guys study guide today. It's going to show up in WebAssign as a homework assignment there. But remember, the point of the study guide is not the WebAssign stuff. You need to do the problem in WebAssign, whatever. But the main point is for you to write out your solutions, scan and submit those on Canvas. It's the scans that get you credit for the study guide, like the 25 points in the syllabus comes from your scanned work. You want to do that as soon as you can so I have a chance to get in there and give you a little bit of feedback. SG Study Guide 1 will open today. Submit scans of SG work to Canvas ASAP so I can give you feedback. Basically, I'll go in and pick a couple problems. I'll grade those as though they're test problems. I won't be looking super closely at everything because I don't have time to do that. But I will take a general look at your work and say, hey, this all looks really good, or hey, I noticed you make this particular algebra mistake a couple times. Be careful about this, that sort of shit. Today is all about the chain rule, which is section 3.1, section 3.4. We're going to look at some consequences of the chain. We're going to look at the chain rule itself. I'll prove it for you. Then we'll solve a handful of simple problems. Then we'll look at some slightly more complicated consequences of the chain rule. And we'll solve some more extreme cases where interesting things happen that aren't entirely obvious. Only one place to start. I should say let epsilon be greater than 0, but theorem, chain rule. This says if, if f and g are differentiable, and u is equal to g of x, then the derivative d dx of f of u of x, we don't even need to say, if. Why not? Yeah. Then this is just equal to f primed of u of x times u primed of x. Yeah, don't even worry about this. Let's just say if f and u are differentiable. This is cleaner. So f and u are both differentiable functions. That's the idea. If you want to differentiate a composite function, the way you do that is by differentiating the outside, leaving the inside alone, then multiply by the derivative of the inside. That's the mnemonic. Mnemonic is differentiate the outside leaving the inside alone, then multiply by the derivative of the inside. I have no idea how to spell the word mnemonic. I know there's an M in there somewhere next to an N in a weird place, so please don't judge me for this spelling. But that's the idea. That's the idea. Let me prove this for you. The proof is not bad. Maybe first I'll do a quick example so you can get an idea. Like if I want to differentiate the cosine of x cubed, my inner is x cubed, my outer is cosine. So first I differentiate the outer, leaving the inner alone. The derivative of cosine is negative sine, and I leave the inside alone. And then I multiply by the derivative of the inside. And I like to write it out like this. So this would be negative sine of x cubed times 3x squared. That's it. So, very, very simple example here to give you an idea of what we mean by this. Let's look at the proof. The proof I'm going to give you here is due to Cauchy, the 1700s. And it actually isn't 100% rigorous, but it's very, very close to being rigorous, just requires a tiny modification. But let's see. So, if capital F of x is equal to little f of little u of x, then capital F primed of x is the limit as h goes to 0 of capital F of x plus h minus capital F of x all over h. So now that I think about it, I don't know if I've ever gone through this proof in the x plus h notation, but we'll see how this shakes out. If we get into trouble here, I'll admit it, I promise. So capital F of x plus h, that's little f of little u of x plus h minus little f of little u of x all over h. And then the idea here is that we're going to multiply and divide by little u of x plus h minus little u of x. So like over here, I'm going to multiply and divide by some quantity. It's of course the same as multiplying by 1, so it's not going to change the value of the expression. But it'll be one of these things where, just like the other proofs of our differentiation rules, we can regroup terms. So this will be lim h to 0, f of u of x plus h minus f of u of x over h times u of x plus h minus u of x over u of x plus h minus u of x. Certainly no fuckery so far. This is just 1. I'm just multiplying this whole expression by 1. But then I'm going to group some terms. And the grouping of the terms is going to be evocative of the derivatives that we are going to calculate. This will be lim h to 0. Remember how these fractions multiply? We have to pretend like the top and bottom of all these fractions are in parentheses. I'm going to shuffle this piece over here, and I'm going to shuffle this piece over here. So I'll get f of u of x plus h minus f of u of x all over u of x plus h minus u of x times u of x plus h minus u of x all over h. Everybody sees what I did there, right? You imagine multiplying these two fractions together into one big fraction. The denominator would be h times this difference. And then I just flip the order of multiplication in the bottom. And then I split the fractions back up. We should recognize what this piece is going to do. This piece is a little more complicated. So what I'll do next is just give the limit to each of those pieces separately. I've got lim h to 0, this piece, times lim h to 0, this piece. This piece is immediately u primed of x. This piece is less obvious. Here, if I think of, what should I do? If I think of this difference here as being like, I don't know, h2, then this is like, it's harder to see. Maybe I should just claim this to be what it is so I don't get us into any extra trouble. This is f primed of u, treating u as its own variable. See, as h goes to 0, this bottom, it goes to u of x minus u of x, which is 0. And this top goes to f of u of x minus f of u of x, which is also looking like 0. This is a difference quotient, but with u as the variable. And over here, this is the normal difference quotient for u primed of x. So it's the derivative of the outer, leaving the inner alone, times the derivative of the inner. That's the game. Now the justification to get this guy from here to here in this notation is a little bit rough. Like the way I usually do this is with the other definition of the derivative. It falls out a bit more cleanly because it's not obvious that this is behaving the same as an h, or that this is going to behave like f of u plus delta u, but it does. So we can consider this, I hope, at least moderately convincing. A full proof with all the details can be found on my notes page here. Ooh, no, don't do it. Damn it. Sometimes Canvas, you make me hate you. Should have the chain rule in here somewhere. Let's see, does he do it any? No, difference, binomial, product, quotient, implicit differentiation. Yeah, here we go. This is looking chain rule-y. Oh no, product rule. Lazy proof of product rule. Chain rule, here we go. Right, so here's u primed. And this drops out exactly how we would expect it to. But then he defines an auxiliary function to get around this. Yeah, it's a little bit shisty. It does work. It's not ideal. I don't think going through these details are going to help anybody here. There's a better way to do this. I can post a better proof of the chain rule if you like, but this is basically the vibe, right? This is like a difference of f of u's over a difference of u's. So this is going to be f primed of u, and this is the regular derivative definition for u primed of x. This piece is nice and simple. I'll call this a proof. We'll say this is good enough. It's not quite there, but it's 99% there. Okay. So again, our mnemonic, differentiate the outside, leaving the inside alone, then multiply by the derivative of the inside. So let's give ourselves some functions that can be understood as composites and see if we can calculate their derivatives. Let's find d dx of tangent of x squared plus 3x minus 2. Let's find d theta of e to the sine theta. Let's find dz of cosine of 1 over z. This is a good start. So in this first guy, I have an inner here, right? And an outer. So my inner, you can think of it as u equals x squared plus 3x minus 2. And my outer, f of u, is the tangent of u. So what I need to do is differentiate the outer, leaving the inner alone, and then multiply by the derivative of that inner function. So when I differentiate this outer function, tangent, leaving the inside alone, I'll get secant squared. And then what's inside secant squared? Well, I just leave the inside alone, x squared plus 3x minus 2. But I need to multiply by the derivative of the inner. That's the derivative of x squared plus 3x minus 2. So I'll write that as this thing primed. And then we compute the second piece there. So this is secant squared of x squared plus 3x minus 2 times the derivative of x squared plus 3x minus 2 is 2x plus 3. And I want to be clear, the 2x plus 3 is not inside the secant function. Everybody comfy with this guy?
Is it fine if we leave it in that form, or do we have, for like, say on a test for our final answer, would you want us to multiply it for it to be like 2x secant squared x squared plus 3x minus 2 plus 3 secant, like?
I would leave it like this. More often than multiplying these things out, we want to factor them. So this is actually nicer than what you'd get if you distributed it. The only, like, if you're talking about notation taste, what kind of looks nicer, moving the polynomial piece 2x plus 3 out front, so it's clear that it's not a part of the inside of the secant. This is the only sort of thing I would consider doing there, but I wouldn't distribute.
Okay.
All right, so what about this next guy? What's my inner and what's my outer?
Sine squared is the sine theta is the inner, e to the x is the outer.
Good,
We did.
yeah, or I would write it as e to the u. That way we can kind of think about u being sine theta, f of u being e to the u. So you can imagine stringing these together, chaining them together. That's the chain rule. So if I want to differentiate this thing, then I should differentiate the outer, leaving the inner alone. If you differentiate e to the u, you just get e to the u. So this is e to the sine theta. But then I need to multiply by the derivative of the inner. And that's going to give me e to the sine theta times derivative of sine theta is cos theta. And that's it. Not too bad, right? On this last guy, my inner function is 1 over z. So I'd say u is 1 over z, which is z to the negative 1. And then my outer f of u is cos u. So again, I differentiate the outer, leaving the inner alone. Derivative of cosine is negative sine. So I'll have negative sine of 1 over z. And then I need to multiply by the derivative of the inner. So I would just write that schematically as 1 over z prime. The derivative of 1 over z, I should think about this is really a power rule thing. So it's going to be negative 1 times z to the negative 2. So this is negative sine of 1 over z times negative 1 over z squared. And this is a case where I can do some meaningful simplification. These two negatives, these are all being multiplied. So I would say that this is the same as the sine of 1 over z times 1 over z squared. And if you wanted to, you could write that as a bunch of different ways. You could write that as sine 1 over z all divided by z squared. Or you could bring the 1 over z squared out front, all of which are equally valid. So these are some gentle examples. Questions on any of these? Okay. So you guys remember from Thomas's lecture last week, the derivative of the natural log, right? We kind of snuck this in here before we knew what it was. Thomas told us that the derivative of ln x is 1 over x, and then we use that as a part of a product rule example. I would like to now convince you that the derivative of ln x really is 1 over x by using the chain rule. Technically, it's implicit differentiation, but it's really just the chain rule. So let's do it. Claim. If y equals ln x, then y primed equals 1 over x. Proof. Y equals ln x is equivalent to saying e to the y is equal to x. Right? This is the definition of the natural log. So now we can apply d dx. we get d dx of e to the y equals d dx of x. On the right-hand side, d dx of x is 1. On the left-hand side, the variable here they don't match, right? This is like e to the y, but I'm differentiating with respect to x. Well, remember, y is a function of x, right? Y is right here, it's ln x. So this is really a chain rule thing. Let me write this out. This is d dx of e raised to the ln of x. And now I apply the chain rule. d dx, my inner here is ln x, my outer here is e to the stuff, right? So this is going to be e to the ln x times the derivative of ln x. Or if you wanted to, you could just write a y primed here. Either way, it doesn't matter. But e to the ln of x, this piece, this is just x. Rules for logarithms. So this is x times ln of x all primed equals 1. Divide both sides by x, and you declare victory. Ln of x all primed equals 1 over x. Or again, if you wanted to write y's here instead, you could skip this line and just write y primed e to the y, and then you get the same thing. But yeah, that's the idea. In other words, i.e. d dx of ln x really is just 1 over x, as claimed by Thomas. Thank goodness, mathematics works. Okay. Some other fun things we can do. So we're going to get practice with stuff like this, implicit differentiation, more down the road. It's just one example of a fun way to use the chain rule. But let's work some harder chain rule problems. One of the fun things to do is to learn how to differentiate arbitrary exponential functions. So we know that the derivative of e to the x is e to the x. But what about things like d dx of 2 to the x? Or d dx of 1/3 to the x? Or more generally, maximally generally, I guess, d dx of b to the x. The trick that'll let us get these from this is an algebra trick. A to the b, regardless of a and b, is the same as e raised to the natural log of a to the b, right? Because the e and the ln kind of undo each other. They cancel each other. People learn it all sorts of different ways. They're inverse functions. And then according to rules for logarithms, up here, the natural log of a to the b is b times the natural log of a. Remember, you have this rule for logs that says, yeah, powers inside of logs can come down as multiples. So that b can come down here, but it's all still in the exponent of e. So this is a nice algebra trick. Therefore, d dx of, let's say, 2 to the x, this is the same as d dx of, well, imagine this is a 2 and this is an x. Then this would be 2 to the x, and that should be the same as e raised to the x times the natural log of 2, and it is. Now the natural log of 2 might look like a function, but it's just a number. It's like 0.6, it's just a number. And to make it more evocative of that, I'm gonna write it in front of the x. So it's like e to the 5x or e to the 6x, it's e to the ln2x. And I can differentiate this using the chain rule. So this first step is by our algebra trick. And now I differentiate using the chain rule. So this whole thing is my inner. We can write it over here. My inner is u equals ln of 2 times x. My outer is f of u equals e to the u. So when I differentiate, I'll differentiate the outer, leaving the inner alone. That means I'll get e raised to the power of natural log of 2 times x. And then I'll multiply by the derivative of my inner, which is the derivative of natural log of 2 times x. So all of that primed. This is by the chain rule. What is the derivative of natural log of 2 times x?
One over 2x.
Tempting, right? But what if it was just 2 times x? What's the derivative of 2x?
2.
2.
2. If it was 5x?
5.
And remember, ln2 is a constant, just like 2 and 5. So the derivative of ln2 times x is just ln2 because he's a constant. We don't actually need to differentiate the natural log here. This whole piece is just a constant. So this is a constant multiple. So we differentiate it the same way we would differentiate 5x or 7x or 10x. The x differentiates to 1, the constant multiple comes along for the ride. So this is e to the ln of 2 times x times ln of 2. And then finally, e to the x times natural log of 2, that's 2 to the x. So this is 2 to the x times the natural log of 2. Pretty slick. So the derivative of 2 to the x is 2 to the x times the natural log of 2. What do we think the derivative of 1/3 to the x is? Let's look for patterns. If the derivative of 2 to the x is itself times the natural log of 2, then the derivative of 1/3 to the x should be
1/3 to the x is the natural log of 1/3.
beautiful. Yeah, that's perfect, Julio. Thank you. 1/3 to the x times the natural log of 1/3. And more generally, the derivative of an arbitrary base exponential b to the x will be b to the x times the natural log of that base, b. And if you check, this works great with e to the x also. The derivative of e to the x is e to the x times the natural log of e. It just happens to be the case that the natural log of e is 1. So this box formula down here we should remember. While we're talking about generalizing derivatives of exponentials, I'll hold here just for a second, those who are writing. Something we've used a few times now, but I haven't written down in its full generality, I'm going to turn the page now, is how to differentiate e to some stuff. So the derivative of e to some shit is always going to be e to that shit times the derivative of the shit. Here, the assumption is that the shit is a function of x. So for example, d dx of e to the x squared would be e to the x squared times the derivative of x squared, which is e to the x squared times 2x. Or if c is any constant, let's say a is any constant, the derivative of e to the ax would be e to the ax times the derivative of ax, should be e to the ax times a. Yes, sure, sorry. Is that better? Cool. So this rule is pretty useful. It is just the chain rule, but specifically this instance right here, we use this so much. Like there are many functions in the world, or many real things in the world that are modeled by functions of this form, e to some constant times x. Lots of them, like pretty much all natural growth phenomena, all population growth phenomena, limiting cases of all interest phenomena. So we run into these a lot. This guy, e to the x squared, and his buddy, e to the negative x squared, they're also very common in statistics. They're the normal distribution with standard deviation 1 and mean 0. So these are very common. What other fun shit should we look at? I guess we should look at, yeah, Putnam problem. Not Putnam problem, but a kind of a competition style thing here. So let's talk about how I could differentiate the following polynomial. Let me use a different notation here a little bit. Let's say d dt of t squared plus 1 raised to the power of 2021. I have some options here. Option the worst I could multiply this all out and then use the power rule. That's like t squared plus 1 times t squared plus 1 times t squared plus 1 times t squared plus 1. All of this written 2021 times, and then use the power rule. Just to be clear, it's an option. It's not a good option. If that was a small power, like a 2 or a 3, it would probably be the best option. But that power is enormous. I would, the probability of me multiplying all of this out without making a single mistake before we all die is pretty slim. It's highly likely I would make a mistake. So let's not do that.
So like you could use the chain rule, right? If
That's
if t squared plus 1 is equal to x, and then x to the 2021 would be,
So let me go through one other option before we get to that. Option less bad, we can use the product rule. But that would require 2021 applications of the product rule. It's not as bad, but it's still pretty bad. If you jumped in and started differentiating this massive product using a bunch of product rules, you would notice a pattern after like the third or fourth one, and you'd be able to write down the answer. Still sucks though. So yeah, option the best is exactly what Julio was just saying. Use the chain rule. If I want to differentiate t squared plus 1 to the 2021, my inner function is the t squared plus 1, my outer function is the power. So if I were to differentiate this power, kind of like put your finger here and pretend like that's just the variable, then we would get, you bring the power down, I leave the inside alone, and reduce the power by 1. So you kind of cover up the inside. This looks like the derivative, right? That's f primed of u. And now we need to remember to multiply by u primed. So what we'll get here is 2021 times t squared plus 1 to the 2020 times 2t. And I think for notation purposes, it's nice to combine the constants out here. So 2 times 2021 would be 4042. This is 4042 times t times parentheses t squared plus 1 to the 2020. So if we went with either of those crappy options, we would be sitting here at least for the rest of the day before we got our result. But the chain rule does it in a second. Does it very, very quickly.
Yeah, that's slick.
It is, right? I like it. I'm a big fan. Some other stuff that we can do now that we weren't able to do before is differentiating powers of trig functions. Now we can use that to discover all sorts of fun things. I'll give you an example. Simple example first. So what if I want to find the derivative of sine squared? Well, I need to remember what that notation means. That's sine of theta all squared like this. So the derivative, I kind of covered up like this, right? I'm going to differentiate the outer, that's that square. So the 2 is going to come down and be replaced by a 1. Leave the thing under my finger as sine theta, but then multiply by the derivative of sine theta. So this is going to be 2 times sine theta to the 1 times the derivative of sine theta. And this is why I write my primes really bold so they don't get confused with 1s. So that's 2 sine theta, and the derivative of sine theta is cos theta. Now, a neat fact, you may or may not recognize 2 sine theta cos theta. This is actually an identity. Sine 2 theta is 2 sine theta cos theta. So if we wanted to, not that we have to, we could write this as sine of 2 theta. And that means that the function f of theta here, sine squared theta, satisfies a neat differential equation. This is not something you need to know for the class, but this means that f theta equals sine theta satisfies the weird ordinary differential equation, ODE, f primed of theta equals f of 2 theta, which is very strange. Actually, no, I might have to take this back. Yeah, sorry. Means that sine theta on its own, oh no, we almost got this. Yeah, sine theta on its own satisfies the equation f squared of theta equals f of 2 theta. Yeah, that's a weird one. F squared primed. Fuck it, it's weird. You can cook up weird differential equations, right? How should I, what's the nice way to say this? Sine satisfies y, the square of y prime. Yeah, here we go. All right, I'll get this right. F primed of theta, or f squared theta primed equals f of 2 theta. There it is. So if you square the function, then differentiate it, you get the function with a 2 subbed inside. There's strange things like this, weird differential equations. Not relevant to the course, but just a funny observation. Some other things we can do now that we couldn't do before. Let's look at kind of chaining these together. Find d dx of let's do tangent cubed of x squared. This is an example of a derivative where you're going to need multiple layers of the chain rule. So I would begin this guy by saying, okay, that's d dx of tan of x squared all cubed. So kind of my outermost thing here is the cube, and then coming in a layer is the tangent, and then coming in a layer is the squaring function. This is kind of why we call it the chain rule, because we're going to chain all of these derivatives together. So I come in one layer at a time. I differentiate the outermost thing, and I leave the inside stuff alone. So this will be 3 times tangent of x squared left alone to the 2. And then I multiply by the derivative of the inside, which is tan of x squared. Now I have to continue with this piece, right? Just linking together the next layer. So I have 3 times tan of x squared all squared times the derivative of tangent of x squared. That's a chain rule thing on its own. So here I will differentiate the outside, leaving the inside alone. That's the derivative of tangent, which is secant squared, so I'll secant squared of x squared, and then multiply by the derivative of the inside. And now finally, I can resolve this last bit of derivative. So I'll have 3 times the tangent of x squared squared times secant squared of x squared times 2x. And this first piece we can write more nicely as 3 tan squared of x squared. So you get 3 tan squared of x squared times secant squared of x squared times 2x. Neat stuff, right? So let's take a second with this, make sure we're comfy with it, and then I'm going to show us a few examples combining the other rules, like product rule and chain rule, quotient rule and chain rule. You can kind of think of it like an onion. You're kind of peeling off one layer at a time. So from here down to here, all I did is really differentiate the cube, the power on the outside. We can, yep, we can bring the 2x out front, and that would be the polite thing to do when we have these. We like to write the polynomial piece out front. This would be 6x tan squared of x squared times secant squared of x squared. Yeah, that would be the nicest way to write it. So we sort of peel off that outer derivative, leaving the inside alone. And then we say, all right, I'm just going to multiply by the inner derivative, whatever that is. And then this guy turns out to be a chain rule thing himself. So we differentiate the outer function there, which is the tangent. He becomes a secant squared, leaving the inside alone, and multiply by the derivative of the inside. And by this line, I would say you could stop here. If the problem was just find this derivative, I would accept this as an answer. But then cleaning it up like this is very nice. It's the nice thing to do. Questions on this fella? All right, I'm gonna move to your book for a few examples here, see what we got. They have a few fun things. Yeah, these are important. We should look at these. Maybe before that, let's look at one other fun thing. E to the square root, nested roots. What's fun here? We should look at something involving a square root. Let's do this guy. So I want to find y prime, where y is the square root of 4 minus e to the 2x. Note, the square root of 4 minus e to the 2x is not 2 minus e to the x. Even though the square root of 4 is 2 and the square root of e to the 2x is e to the x, these are not equal to each other. Square roots never play nice with addition or subtraction. It's one of the big headaches in algebra. So I can't just like say, okay, I'm gonna simplify like this and then take the derivative. That doesn't work. But what does work is the chain rule. So y here, the square root of 4 minus e to the 2x, that is the same as 4 minus e to the 2x all raised to the 1/2 power. So y primed is d dx of 4 minus, 4 minus e to the 2x all to the 1/2, like this. So my inner here is like 4 minus e to the 2x, and my outer is the 1/2 power. So first I'll differentiate the outer, leaving the inner alone. That'll be 1/2 times 4 minus e to the 2x to the negative 1/2. That's the derivative of the outer. All right, if I differentiate the 1/2 power, I get 1/2 times that thing to the negative 1/2, but now we need to multiply by the derivative of the inside. So this piece is done. But now I need to turn my attention to this guy. The 4 will differentiate to 0. So I'll have 1/2 4 minus e to the 2x to the negative 1/2 times the derivative of 4 is 0. I'm not worried about that. But the e to the 2x, that's a chain rule derivative on its own, right? And then the derivative of 2x is just 2. So this is 1/2 4 minus e to the 2x to the negative 1/2 times negative 2 e to the 2x. This negative is this negative. The derivative of 2x is 2. And we can put these pieces together. The 1/2 here and the negative 2 here. E to the 2x. And then 4 minus e to the 2x to the negative 1/2. I can cancel the 2's here. And I'll get negative e to the 2x over the square root of 4 minus e to the 2x. Right, this negative 1/2 power brings that term downstairs. Downstairs because the negative. And then the 1/2 power is a square root. So this is the derivative of the square root of 4 minus e to the 2x. Questions on this one? As a usual rule, the chain rule takes some getting used to. Even if you've seen some examples in the past, the chain rule can be a little bit jarring when we ask you to use it in full generality. Multiple layers of the chain rule, like we saw here in the last problem, can be daunting. And sometimes it's a little hard to see what your inner and outer functions are. That's your first few homework problems on the chain rule. Just ask you to identify the inner and the outer. So yeah, that's that. I wanted to look at something that combines this with the product and quotient rules. So that's the last few examples I'm going to do for you guys today. I'm going to tab away to the book for a second. Any last call for questions on this fella? Any of the steps, the calculation, the algebra, the derivatives. Happy to look at any piece that you guys want to see. Okay. So what did we say was important? This is called the damped harmonic oscillator, hugely important. Let's do that. What else is a big deal? We can try something a little more abstract like that. This one's in your book. That's a good problem. I don't want to spoil it in your. Yeah, okay, let's do the damped harmonic oscillator. turns out that a lot of differential equations have solutions that look like this. In fact, if you take an arbitrary linear constant coefficient differential equation, odds are very good that the solutions will be of this form. For some choice of constants a and b. Firstly, we need the product rule, right? Because the kind of outermost thing that's going on here is that this is a product of two functions. Then each one of those functions requires a chain rule to differentiate. So let's get started. F primed of t should be d dt of e to the at times sine of bt, which is a product. So I'll use the product rule. This is the derivative of the first times the second plus the first left alone times the derivative of the second. As we've seen a few times, e to the at has derivative e to the at times at primed. That's the chain rule there. And then this sine of bt is chilling plus e to the at chilling. Now the derivative of sine bt, that's also a chain rule thing. I differentiate the outer there. Sine differentiates to cosine, leave the inside alone. And then I multiply by the derivative of the inside. So if I compute my little derivatives now, this is e to the at times the derivative of at, which is just a. And that's being multiplied by the sine of bt. Over here I have plus e to the at cos of bt times the derivative of bt, which is just b. And I can factor an e to the at out. That's a nice thing to do that. And what I'm left with is a times the sine of bt plus, right, a times the sine of bt plus b times the cosine of bt. And yeah, it turns out if you take a constant coefficient second order linear ODE, the solutions will always be in this form for some choice of constants a and b. Now, second order linear differential equations happen to be exactly what you need to describe motion in the physical world, like Newtonian mechanics. So these are hugely important. Questions on the derivative calculation here, any one of these steps? I can annotate this was a product rule. And then this is chain rule. And then this was just algebra in the last step. All right. I have just a second or two longer to mess with you guys' heads. And so I'd like to look at, well, no, it's Wednesday, right? It's a little early for me to drop the next week stuff on you. So maybe let's look at something like this. Or so here's a constant coefficient second order linear ODE, and they're asking about solutions to that. That's fun. Well, it looks like fun. I don't know. These are all a little boring. We haven't done anything involving the quotient rule yet. I don't know if that's really worth it. The quotient rule kind of sucks. Let's take a look at this. So let's define h of x to be the square root of 4 plus 3 times f of x. And suppose f of 1 is 7, f primed of 1 is 4. And see if we can find h primed of 1. The trick here is to work symbolically. So h primed of x, I know is d dx of this thing, which is d dx of 4 plus 3f of x being raised to the power of 1/2. And now in here, I can think of this as my inner and the 1/2 power as my outer. So I'll get 1/2 times 4 plus 3f of x to the 1/2 minus 1, which is negative 1/2. And then multiply by the derivative of the inner, which is 4 plus 3f of x. And the obvious challenge is I don't know what f of x is. But I can take the derivative symbolically. This will be 1/2 4 plus 3f of x to the negative 1/2 times the derivative of 4 is 0. The derivative of 3f of x is 3f primed of x. So symbolically, I can write this derivative as 3f primed of x over 2 times 4 plus 3f of x to the negative 1/2. And if I'm really feeling algebra fancy, then I would write this as 3f primed of x all over 2 times the square root of 4 plus 3f of x. And that's h primed. So they want to know h primed of 1. That's going to be 3 times f primed of 1 over 2 times the square root of 4 plus 3 times f of 1. And we were told, remember, that f of 1 is 7 and f primed of 1 is 4. So now I just plug those bits in. This is 3 times f primed of 1 is 4, divided by 2 times the square root of 4 plus 3 times f of 1 is 7. So that's 12 divided by 2 times the square root of 3 times 7 is, oops, sorry. 3 times 4 is 12, divided by 2 times the square root of 3 times 7 is 21, plus 4 is 25. So this is 6/5. Right, 12 divided by 2 is 6, square root of 25 is 5. And that's the game. So this is the chain rule. It's not terribly hard to work with once you get practice. I know that there is a diversity of backgrounds in this class. Some of you guys took calculus in high school. Some of you guys have taken calculus elsewhere. And for some people, this is our first time ever seeing the chain rule. If this is your first time ever seeing the chain rule and this looks scary, don't feel bad. It always looks scary at first. And I promise you, no matter how confident anybody you talk to seems about this, it scared the shit out of them the first time they saw it too. Don't feel overwhelmed. Remember, it's just like an onion. You peel off one layer at a time. Differentiate the outside, leave the inside alone, then multiply by the derivative of the inside. As long as you remember that, you'll be okay. The homework for this week shouldn't be too overwhelming. There's not a bunch of conceptually deep stuff in there, but plenty of practice using the rules we've talked about. Integrating, I shouldn't say integrating, but involving derivatives, chain rule derivatives with trig functions, and of course, all the rules from the past weeks. I will go ahead and release your study guide 1 today. It's going to take me a little while to put it together. I've got an office hour from 1 to 2. As soon as that study guide drops, you're welcome to begin working on it. I recommend that you work on the study guide after finishing the homework or after finishing most of the homework, because there will be some problems in there that will be difficult if you haven't practiced them yet. But as soon as you feel comfy with this week's homework, go ahead and start working on the study guide as well, and then submit the written work for the study guide to Canvas as soon as you can. That way I'll be able to get in there and say, this all looks wonderful, or maybe you need to consider rewriting these things a little bit differently, whatever it is. So you're not surprised by the critiques I have to offer on the exam itself. Remember, the exam is a week from today, next Wednesday, which is the 10th, right? Yeah, 1 week from today. So be mindful of that. The study guide needs to be handed in, like your scans need to be submitted by the 10th. That's the latest I can take them. So you have a full week to grind on the study guide. If you do want to talk to me about anything, you can come by my office hour. Otherwise, I'll see you guys on Friday when I will be introducing the next section, which is implicit differentiation, and we'll work some more problems with the chain rule. Any questions for me here before we go? Alrighty, guys, I will see you on Friday. Have a nice afternoon. Whoa, all right, there we go. Take care.